So in the first lecture segment, we left off looking at how an enzyme binds to the substrate at the place called the active site and then moves and crunches down on it, and that is called induced fit. And that part of that will move and put stress on the bonds of the substrate to either make bonds form or break or both. And so that's the catalysis of the reaction. What I want to point out is that even though the active site is a certain little niche of a particular shape on the enzyme, there are other little niches that are on a protein. So for example, let me get my pen. So for example, like on this drawing, maybe right here, you know, these little niches, the ones that we can see, and I'm sure there's some we can't see if we rotated this structure around, but there are other little niches on enzymes, and some of those can be places where other molecules can bind, attach. And an example of that would be inhibitors. Some inhibitors, all inhibitors are substances, molecules that bind to an enzyme to slow it down or make it decrease its activity, its ability to speed up a reaction. Competitive inhibitors would be a molecule that actually enters the active site and blocks it so the real substrate can't get in. And obviously that would stop the reaction from occurring. But there are these non-competitive inhibitors, and this is kind of what I was thinking of in the previous slide, that will bind to these other sites on the enzyme. And any site on an enzyme that something can attach to, but it's not the active site, can be called the allosteric site. Allo means other, steric is shape, allosteric, other space, I think is more accurate. Steric is like space, but another site, another place for something to attach. So either an inhibitor binds directly to the active site, and of course that immediately stops the reactions from happening, but it can also attach somewhere else. And usually when that happens, it will change the shape of the enzyme overall so that even the active site is not the right shape. And that can stop the reactions from happening. So this is a drawing of this. So an inhibitor can bind on the back end of an enzyme. Let's say the active site is here, but any other site could be called an allosteric site. And so you can see when this inhibitor binds here, it changes the shape, including the shape of the active site, so that the real substrate can't enter the active site and undergo whatever chemical reaction was supposed to happen there. In a similar way, there are enzymes that have allosteric sites, and when a molecule binds to the allosteric site, it can actually serve to open up the active site from a position, a shape where it was originally in a closed shape. So we call that an activator. So we name the molecule, in this case the red square, based on what its effect is on the enzyme once it binds. If it inhibits the reaction or stops the reactions from happening, it's an inhibitor. If it causes more reactions to happen, we call it an activator. And different enzymes, some enzymes have both activators and inhibitors. It's possible. Other things that are needed for enzymes to function. Most enzymes require bound somewhere on the molecule these things called coenzymes and cofactors. Coenzymes are fairly medium, well, not large, but medium-sized molecules. And you would typically, in common language, we call them vitamins. So coenzymes, think vitamins, but we're going to use the term coenzymes. And cofactors, think minerals. So vitamins are these organic compounds you can see in this chart here. You do not need to memorize the names or the structures, but you probably recognize the names. but they are organic molecules. You must have small amounts of these in order for enzymes to work properly. Ions, metal ions, are cofactors, but we commonly refer to them as minerals. So iron, magnesium, zinc, copper, these are metals that you need small amounts to bind to your enzymes in order for them to work properly. So in some ways they're like activators. And if you don't have the right amount, if you don't have enough coenzymes or cofactors, that can cause your enzymes to not be able to catalyze their reactions. All right, so where are we going with all this? The idea is that chemical reactions convert materials from reactants to products, but sometimes they require energy or sometimes they release energy in that process. And really what a cell does is hook these all together, all these enzymatically catalyzed reactions. They are actually hooked up in series in the cell. And so a series of reactions can be referred to as a biochemical pathway. So cellular respiration is a biochemical pathway, and photosynthesis is a biochemical pathway. And so you don't just have one enzyme, you have multiple enzymes. I would say cellular respiration, you have probably, I don't know, 20, at least 20 enzymes just for the very bare bones pathway. Photosynthesis, somewhat less, but you have multiple enzymes. But what happens is the cell has an initial substrate which gets converted into a product, but the product of the first enzyme is the substrate for the second enzyme. And so the second enzyme takes that, in this case yellow triangle, and converts it into the pink square, and the pink square is the product of enzyme 2, but it's the reactant for enzyme 3, or the substrate for enzyme 3. And so this conversion process happens in this sequential way to get to a final product. So, and what we're not showing here is energy going in and out as well. So it's not just the molecules being converted, but it's also energy going in to form bonds and energy being released as bonds are broken, because all chemical reactions involve making and breaking of bonds. And so all of that together makes up the biochemical pathway. Not just here, we're kind of paying attention just to the molecules themselves, but also the energy transfers and transformations. Now, cells are very good at managing not only their molecules, but also their energy. And so when we talk about regulation, the word regulation in biomedical science, it means the cell managing which reactions are going to happen when. Because not all the reactions that are possible in a cell are going on at all times, especially in multicellular organism, for example. When you're a child, there are certain chemical reactions that are happening at high levels, like cell division and all the things that lead to cell division, building of a lot of materials. You have to eat a lot when you're a child because you're building all kinds of new structures and you're growing. And that would be different than the reactions that are happening in the cells, let's say after puberty. So the cells of an organism, of a multicellular organism, are regulating or managing which reactions are happening or not happening. And one way that works in terms of controlling reactions it's a very common mechanism. It's called feedback inhibition. So when a cell has a certain enzymatic pathway, a certain biochemical pathway, a series of reactions catalyzed by enzymes, what often happens is enzyme 1 converts green triangle into purple rectangle. Enzyme 2 converts purple rectangle into blue squirrely thing. Enzyme 3 converts blue squirrely thing into yellow square. Well, however many steps there are, what will typically happen is if the end products, if there starts to be too much of this and the cell doesn't need as much of this end product, what will happen is the end product will act as an inhibitor, an allosteric inhibitor usually, allosteric inhibitor, to one of the enzymes that is part of one of the earlier steps in the same pathway. So when the yellow squares start to pile up, they start to block enzyme 1 in this example from being able to do more. And then that's always going to be a temporary inhibition. It's not permanent. And when the cell starts to run out of yellow squares, then the inhibitor will detach from enzyme 1 and the pathway can begin again. But in that way, it acts as similar to the way a thermostat acts in your house. In your house, the thermostat, when it gets, if you're cooling your house in the summer, when it gets too cool or the right temperature, it shuts itself off because it's got enough cold air that it shuts off, and then as the temperature starts to creep up, it triggers it to come back on. And in that way, it's always in a comfortable zone of having enough of whatever it is, but not having too much. If your air conditioner just ran full strength all the time, it would be too cold. Although I know some of us have a hard time imagining that, but it could happen. Or in this example, if this pathway just ran all the time, you would end up with too much yellow square. So the yellow square ends up acting as an allosteric inhibitor towards one of the enzymes that's actually part of this same pathway. So it's a really interesting and effective way that most of these pathways will regulate themselves, kind of like a thermostat in your house.